Alrighty, y'all. Today we're taking a look at the recitation for Friday, February 4th. Right, and for this one, we're going to start with like 2D motion and vectors. Right. So I'm going to start actually with a real quick review because a lot of this is going to be based in our right triangle trig. Right, so I'm going to draw a right triangle. We'll just do a quick review of that. Right, here's our right triangle. Right, we have our hypotenuse and our two legs. Right, I'm going to call this our angle theta. Right, so we're going to just remember our SOHCAHTOA. Right, where the sine of that theta is going to be equal to our opposite side over our hypotenuse. Right, over hypotenuse. Wonderful. And cosine theta is our adjacent over our hypotenuse. Right, so this is our opposite side, this is our adjacent side, and there's our hypotenuse. And our tan theta is our opposite over adjacent, right? Our SOHCAHTOA. These are very important when we start looking at breaking things into components. I'm also just going to make sure we have a quick review of our good friend Pythagoras and his theorem, right? Fun fact, Pythagoras was afraid of beans and like legumes and stuff. I don't know, right? So it's our leg squared plus our leg squared, so O squared plus A squared equals our H squared, right? These are going to be our best friends once we start getting into breaking things into components. So let's get started with some actual questions then. Right. So we are going in a direction. Right, we're trying to find out. So we're starting at Penn Station, and we're going, it says it goes north on 8th Ave. It's not directly north, right? We're going down in the direction of this, right? So I'm going to take this. I'm just going to move it over here so I can start looking at some, right? So you want to know, we know that this is our 3.3 kilometers that she went down 8th Ave, right? Now we're going to break it into how far east and how far north. Well, if we're looking at, right, here's north-south. Oh, that is not a well, right? There's north-south, and here's east-west, right? Here's just some axes, right? So we know that in the end, she'll have gone this far east and that far north, right? So we're going to break it into these components, right? So if I draw that vector there and that vector there, right, we're given the angle that she's walking at, right? Between north and the avenues, it's 28.9 degrees. So we can mark that as 28.9, right? Now, wonderful news, that's a right angle. Here's our best friend, our right triangle trig, right? We have a leg, and a hypotenuse, and we have this one angle theta, right? So, right, if I take this east vector that I drew, ooh, I did not mean to get all of that. I just want the vector, right? And move it up here. Suddenly, east, I've now set that up as our opposite side. I've set our north as the adjacent side. And our 3.3, that's our hypotenuse. Right? Because here's our theta is our 28.9 degrees, right? So if we want to find out how far east, right, we're going to use our SOHCAHTOA, right? So sine of our 28.9 is going to equal opposite, east, over hypotenuse, 3.3. And I solve this for east, so we get that east equals 3.3 times the sine of 28.9, which is going to equal roughly 1.594831865 kilometers, right? And now we need to find out how far north, right? So that's our adjacent side, so we're going to say that the cosine of 28.9 is north over 3.3. Again, we solve for north equals 3.3 cosine 28.9, right? And that's going to roughly equal 2.889032939 kilometers. Cool. And there's our questions, right? How far east and how far north? Wonderful. Now, we have a displacement vector pointing from the Metropolitan Opera to Carnegie Hall. And now we're going to draw a couple different components on this, right? So we have a couple different ways that we can set up our axes. All right, so I'm going to get this. First thing, it asks for a component in the direction of the Manhattan Avenues and the perpendicular to them, right? So we're going to have our axes are going to be parallel to our avenues and perpendicular, right? So we set up, there's one there, and perpendicular is going this way. Okay, and I'm going to make it approximate right? So here's the axes that we set up. Now let's draw some vectors on this, right? So we're going to draw, I marked them earlier, right? So the red one is going to be our component in the direction of the avenues, right? So we're going to find out generally where it's crossing like that. There's our, I'm still in dotted line mode. There's our component in the direction of the Manhattan Avenues. Erase this now, right? Cool. Now I said that was going to be blue. Now our component perpendicular, right, we're going to do the same thing. I'm just going to pretend I extended this line out more, but I'm not going to do that because I'm a little lazy, right? But, right, there's where that meets. Here's our component perpendicular to the avenues. And I'll erase my dotted lines. Now I'm just going to get rid of these axes for the sake of confusion. Because now we're looking at components along north-south and along east-west, right? So here's the same, I'm going to do the same thing again. I'm going to set up my axes, right, in the north-south direction. And make sure that lines up where I want it. And in the east-west direction. And that's pretty close, right? And I'm drawing this one in purple. Right, so along the north-south axis, that's up here, right? It's the same thing as before. I'm going to find where it would go like that. Oh, I'm still in the dotted line mode. That's not helpful. There's our north-south direction, right? And then in the east-west direction, right, we said that's going to be dark blue. Right, same thing, we're going to get our over to this line, just like that, right? And I'm going to erase all my mess all over this, right? There are vectors. Now I'm going to erase the axes, and I'll bring these component vectors back in, right? Right, so it's just different ways of representing this vector, right? We can break it along these perpendicular axes, or we can break it on these perpendicular axes, and it's going to be the same way of representing that one vector. Cool. Now we have a hiker in a forest walking in a direction, all right? So 5 kilometers due north, right? And 2 kilometers due east, right? 5 kilometers there, and 2 kilometers here, right? And then we're returning back to our starting position, right? So this is going to be our path of the hiker, right? Because there's our north, there's our east, and we're back to the beginning. Now, what direction should he walk and how far? So we're looking for the direction and magnitude of this vector pointing from where we ended back to where we started. Now we revisit our good friend, right? Because we can get the magnitude of this with some right triangle trig, right? We have the leg of a triangle and another leg of a triangle. Let's get us a hypotenuse, right? So it's going to be 5 squared plus 2 squared. Take the square root, right? So that we get the square root of our hypotenuse squared, which is just going to give us the hypotenuse. So our magnitude is going to be about 5.385164807 kilometers. Right? So if I'm just going to borrow this picture so I don't have to keep going up to it. All right. Now I'm going to say, all right, we need to find out, we're going from here to here. So I'm going to find out what angle below east we're going to try to, or below west, sorry, because we're going to the left, is this theta, right? Because that's going to give us the direction we're going. So if we look west and then we turn however many degrees south from there, then, all right, we get to figure this out. So we have, and technically we have all the legs, but I don't want to be doing math with that mess. So I'm going to say that the tangent of our theta is going to equal, all right, TOA, opposite 5 over 2, right? Which means that our theta is the inverse tan of 5 over 2, which roughly equals 68.1985951 degrees, right? So that's going to be our answer, 5.3 however many kilometers, and here's our direction. So we have a magnitude and a direction, so we have a vector, right? And this is south of west. Wonderful. Now we keep going, right? Now the path gets more complicated, right? 3 kilometers due north, then 4 kilometers at an angle 30 degrees south of east, right? So here's east. We're going 30 degrees south of it. We're going to go around there, okay? And that's, we started with 3 kilometers, and now we just did 4 kilometers, all right? And then 5 kilometers at an angle 45 degrees north of west. So now starting from our point over here, here's west, and we're going 45 degrees north of it for 5 kilometers. Ignore how bent and gross that line looks. It's fine. 45 degrees in there. Cool. It's a gross looking picture, but we're going to break each of these vectors into their components so we can add them all together, right? So, right, our 3 kilometers, I'm going to redraw it down here. How far north and how far east for each, right? So we're going 0 east for this one, and we're going 3 kilometers north for that one. Right? So that one's pretty straightforward because we're not going east at all. Right? And now this one starts getting more complicated. So we're starting here, we're going like this. Right? And there's our, break it into a that way component and a that way component. Here's our east. This is our 30 degrees south of east. Right? And this was our 4 kilometers. Right? So what we're going to do, right, we're going to take this vector, move it over here to get our right triangle. Right? So we can relate them all. And that does not look clear what that 4 kilometers is labeling. That's that. Right? So now you get that our opposite side, right, our north direction is going to be our hypotenuse times sine 30, right, because our opposite over hypotenuse would give us sine 30, so we multiply both sides by the hypotenuse to get the opposite side. We're going to do the same thing with cosine, hypotenuse, cosine 30. That's going to give us our north and east directions, respectively, right? So north, it's going to be 2 kilometers, but we're going down, so it's going to be negative 2 kilometers, right? I'm going to say that south is negative for this. All right, and then in our east direction, it's going to be roughly 3.46410161514 kilometers. All right, and that's still positive because we're going to the east, right? Now let's break our last vector into components, right? So we're going this way, and we're going to break it into a this way component and a this way component. And this is going to be our 45 degrees, and this is our 5 kilometers, right? Same thing as always, I'm going to take our vector, move it over here, give us a right triangle, right? And then I'm going to do our same thing as before, where we're trying to find our north direction. So it's going to be the opposite leg from this. So it's going to be 5 sine 45 equals our north direction, right? And then for our x direction, our east direction, it's going to be 5 cosine 45. Right? Sine and cosine of 45 are both the same thing because unit, who remembers our unit circle, right? Right? And we're going to the left, so that's going to be a negative as well, right? So they're actually going to be the same. It's just going to be 3.53553390593 kilometers. This is going to be the same, just negative, right? Because sine 45 is the same as cosine 45. Cool. Now, to find this final position, right, we're going to have to add them all together. So let's add all of our north directions. North is going to be, said it was 3 plus our negative 2 plus that monstrosity, 3 point whatever. Right, and that is going to give us, right, in our north direction, that's going to be roughly 4.5335533905993. Right, and since we ended up with a positive direction, that makes sense. We ended up with a positive because we ended up positive in the end, right? Our net, our adding them all together from beginning to end should have a positive direction, right? And we'll flip that later. Now we do our east. East is going to be 0 plus this mess, right, plus, right, and then we have another negative over here, or negative this mouse, right? And that's roughly going to give us negative 0.0714322908 kilometers, right? So since we ended up with a negative in the east direction, my drawing's a little off. I think this would extend a little bit further, right? Because then from start to finish, it would go just a little bit to the west and very far up, right? So yeah, we have our two components now. Well, that's figuring out how to get from the beginning to the end. Now let's figure out how to get from the end to the beginning. So we're going to flip the direction of the vector, which just means we're going to be going positive in the east and negative in the north, right? So if I'm finding, so really we're going to have negative 4 point whatever north and positive in the east. So now we have our two components of our vector. Cool, let's get the magnitude. All right, so I'm going to square this one and square this one and take the square root, right? Our good friend Pythagoras. All right, and we're going to get a magnitude. Our hypotenuse is going to be approximately 4.536096382 kilometers, right? Now we can do the same thing. We want to find our angle, how to get from here back down to here. So what we're going to do, we're going to set up our triangle. It's kind of a mess. It's going to be obviously either a very big angle or a very small angle, depending on what you're looking at it from. I'm going to say our triangle, right? I'm going to move this vector just off to the side. Make it a little bit more extreme so we can see this, right? There's our, we're going to be going down though. Right? There's our east direction. There's our north direction. Like we said, positive in the east, negative in the north. And I'm just going to find this angle. And I'll move this vector down here. Here's our right triangle. We have our north and we have our east components. So we're going to get that our tangent of that theta that we're looking for. It's going to be our opposite over hypotenuse, which is going to be east over north. So east was said was 0.0714 over 4.5355, right? Opposite over adjacent. So that means that our theta is our inverse tan of that. And again, we can use a calculator for all of our trig stuff. So that's going to give us that our theta is 0.909304011 degrees, right? And that's going to be east of south, right? East of south, right? Because we're going to be facing south, and then we're going to go a very tiny angle towards the east. So here's our answer. There's our magnitude, there's our direction, all good. Now we get to our final question of the day, right? We have a swimmer swimming this fast in still water. They want to swim directly across a river, right? But there's a current in the river with speed, right? If they want to swim directly across, they'll end up drifting downstream due to the current. Therefore, we're going to angle upstream so that we go directly across. So let's draw some pictures, right? So we have a velocity relative to the current, a velocity relative to the shore, right, and a velocity of the current, right? we have the person relative to the water, right? We're saying they're going to be going at an angle in the water. Then we have the current pushing us back this way. Say if I'm drawing my picture kind of like this, I'm going to draw my current going like that, going to the left, just because that's what it made me think of. So I'm going to set my positive over here and my negative over here, right? So the current of the water is going to the left, and we know the person's going to be angled upstream some way, right? We know that, like, in total, their velocity relative just to the shore, we want to look like they're just going straight across. So what we can say is that our velocity of person relative to water plus the water relative to the shore is going to give us our person relative to the shore, right? Which kind of makes sense, right? Because if we have our, like, person to the water and the water to the shore, right, obviously there's some relationship where kind of like our water is our common denominator, so it's going to leave us with our person relative to the shore, which is kind of what we see, right? However far we angle upstream, and the current's pushing us back this way, right? So this is where we're trying to go. This is where the current's changing our direction. That's going to be our net velocity. That kind of makes sense. This is a tricky one to try to conceptualize, right? So our next question is, at what angle must we try to swim in order to proceed directly across the river? Right? So I'm going to redraw my picture down here. All right, we know that we can go 5 kilometers per hour. Yep, 5 kilometers per hour that way. And the water's pushing us 2 kilometers per hour that way. And if I just fill in our right triangle like that, right? So we're trying to find this angle that we're trying to angle upstream. All right, I'm going to call that our theta. That's how far upstream we're trying to go. And you can find a couple different angles, but I'm just choosing to look at this one, right? Because that's going to be, right? That's going to be our easiest, or I think that's going to be the easiest, right? Because I can just take the sine of this. Sine of that theta is going to equal opposite over hypotenuse, which is just going to be 2 over 5. Right? So our theta is our sine inverse of 2 over 5, which is going to be roughly 23.578178848 degrees upstream. Right? Because again, we said since this is downstream, that's going to be upstream. Right? So we're angling that far upstream. And that's going to let us go straight across, right? Because we add these two vectors together, that's going to leave us with a just that way. Right, so whatever angle this theta is at, if I break this, the 5 kilometers per hour, into components, right? If I'm over here, I have this. I break this into my this way and this way component. Our velocity of the water, right, that's going this way. If I'm adding all of this together, right, we get rid of this because we broke it into components, so this is equal. If I'm adding these together, this is going to be the same. Our 2 kilometers is going to be the same as our upstream or downstream component of this. Right? So these are going to be going in opposite directions, so they're going to cancel. That leaves us with a just upwards component, just directly across the stream. All right, if the river is 200 meters across, how long will it take to cross? So, all right, we have a distance. All right, we know that from our one side to the other, 200 meters. That's going to be our, all right, delta y or whatever, that's going to be our final position, right? We say our y final 200 and our y, that says x, y initial is going to be 0, right? Because I'm just going to say that's our 0. So our delta y is just 200, just to simplify things, right? So, right, if we're just looking in just the y direction, right? If this is canceling out, right, I'm trying to look in the y direction. I'm trying to get from point A to point B in the y direction. How fast am I traveling in that direction, right? Because if we're not traveling in this direction, we're not traveling 5 kilometers per hour this direction. We're traveling 5 kilometers per hour this direction, so we're actually going to be going this way, just a component of that, right? So if we have our two, like a leg and a hypotenuse of a triangle, you can say that, right, if we say that our, I'm just going to call this Vy, right, our y velocity. So we're going to get Vy squared, leg of a triangle, plus 2 squared, our other leg is going to be 5 squared. Oh, that looks like an S. 5 squared, right? So if we're solving for Vy, it's going to be 5 squared minus 2 squared, and we take the square root to get our velocity going in the direction we're trying to find out, right? Because if we have how far we're going and how fast we're traveling, we can find our time pretty easily, right? And I'm just going to real quick convert this, right? Because we have, all right, let's just get our Vy real quick, right? So that's going to be roughly 4.58257565. And again, units, kilometers per hour, right? Because that's what this was given in. You could also use, if we wanted to use trig, we could say that the cosine of this angle is going to be equal to adjacent over hypotenuse. So our Vy would be 5 cosine of our angle that we figured out, 23.57, or 5.8 rounded, right? And that's going to give us the same number, because Mr. Pythagoras was pretty smart, and that's, right, there's two ways to get the same number, right? So now we have how fast we're going, and we have the distance that we're traveling. But I see another problem just briefly as I'm writing it in to cause the problem, right? We have this in meters, and this is in kilometers per hour. This is slightly problematic because we want to keep consistent units, right? So I'm going to put this. I'm actually just going to convert the easiest unit to convert, meters. I'm going to convert it into kilometers. So 200 meters, right? And for every 1 kilometer is 1,000 meters. Meters cancels, and we're left with 0.2 kilometers. Cool. Now we have a distance traveled and a speed at which it is traveled, right? We're not accelerating, so we don't have to worry about all of our equations of motion, right? I mean, or we can, right? So our y final equals our y naught plus v naught t plus 1/2 at squared. Right, our acceleration, 0, so you can just ignore that, right? And we said our y naught was also 0, and our y final, we just said was 0.2 kilometers. And our v naught is the same as our v final, just because it's not changing, right? So there's our velocity. So we're going to get that our 0.2 is our 4.5826, again, kilometers per hour in kilometers times time. And if we're solving for time, right, that's just going to be 0.2 divided by 4.5026, right, which is going to give us roughly a time of 0.043643578. And what are our units for this? I wonder, right? Here we were in kilometers per hour, right? So this is going to be, once we got rid of our kilometers, this is going to be hours. So 0.04 hours, I mean, I don't know what that is off the top of my head, so I'm going to do a real quick conversion and get that into something a little bit more understandable, right? So 0.0436 hours. All right, we're going to take that. And for every 1 hour, we're going to get 60 minutes. All right, so we cancel that out. And that's going to give us roughly 2.618614,683 minutes. Cool. But I usually do a lot of stuff in everything's in meters per second, everything's in seconds. So I'm just going to real quick convert it into seconds. Right? That many minutes. For every 1 minute, we have 60 seconds. Right? Minutes cancels, and we're left with 157.11688 seconds. Either any of these answers, that was supposed to be a star, any of these answers would be perfectly acceptable. Just make sure you want to specify your units, because obviously if I said 0.04 seconds, we're not getting across the river in less than a second. Less than a tenth of a second, might I add. Right? Anyways, I hope that you understood most of this recitation. A lot of this trig stuff is very important going forward, especially with solving our 2D motion problems. Let me know if you have any more questions about this recitation or any other problems that you want me to try to explain, and I will do my best to try to explain them because I guess Sydney explains stuff.